This is the problem about shrink fitting, and it says a commonly used method of fastening one part to another part is called shrink fitting. A steel rod has a diameter of 2.0026 centimeters, and a flat plate contains a hole whose diameter is 2.0000 centimeters. And this is the best image I could find. So here's this round piece here that fits into this hole respectively is actually too large, and then you cool it and it will contract, and then you can fit it in there, and when it returns to normal temperature then it will be stuck to that flat plate. As I said, that's kind of the substitute image that I came up with. So the problem continues. The rod is cooled so that it just fits into the hole. When the rod warms up, the enormous thermal stress exerted by the plate holds the rod securely to the plate. By how many Celsius degrees should the rod be cooled? Okay, let's see what we have given respectively, what is being asked for. They're asking by how much it has to be cooled, so they're asking for a temperature difference. They don't tell us what the original temperature is, but we will see from the equation that that is not necessary to know. But instead, we need to know what the temperature difference is, respectively. That's what they want us to figure out. Okay, let's see. What is given is the original diameter. Whoops. D0. Hold on. Might as well write this again here. So D0. What is given is the change in the diameter, delta D. There we go. What else is given is the material, the steel here, and now we have to look at an equation before I write this one here down, and that's the equation on thermal linear expansion, which is delta L equals alpha times L naught times delta T, and of course our delta L and the L naught here, the length, are the diameters and the change in diameter that we have here. By the way, somebody could argue that, well, it happens in 2 dimensions, but still it's a diameter in one dimension, the diameter in the other dimension that needs to change. So the equation is applicable either way, and we only apply it to one diameter, and it would apply to the other one simultaneously. Anyway, what we also know is the alpha, the coefficient of linear thermal expansion for steel, and then what we need to figure out, in this case they're asking what the delta T is, so we're going to do the algebra. Delta T equals delta L, which is the 2.0026 centimeters, I believe it said in the problem. Yes. Okay, I actually did make a mistake a moment ago here. Of course, that is the 0.0026 centimeters, that delta L or delta D, because that's by how much it has to shrink in order to fit into the hole. And then divide that by the alpha, which we look up in the book, and it's given as, for steel, where did it go? I'm trying to find, they were iron or steel, 12 times 10 to the negative 6, and the unit on that is per Celsius degrees. And then we also have to divide by the original length, which would be 2.0026 centimeters. Notice that we don't have to convert to meters on this one, because this one is in centimeters, this one is in centimeters, so the two divide out, and the only unit that survives is the reciprocal of Celsius, which is the unit for the alpha, and because it's a reciprocal and this thing is in the denominator, it goes back to the numerator, and we have a typical Celsius degrees here as the unit. This one here is going to come out to a positive number, even though they're saying it's cooling. I mean, if you wanted to have a negative number, I guess you could call this one here. It has to shrink by 0.0026 centimeters, so you put a negative in front of it because it's shrinking, and then you would also come up with a negative temperature. But either way, you know, you're going to come up with 100 some degrees. Top of my head is what it is, and you can deal with that as either saying that's a positive number or it's a negative number. Either way. This is the problem on these two thin strips that kind of look like a bimetallic strip, a little bit different. As the drawing shows, two thin strips of metal are bolted together at one end and have the same temperature. One is steel and the other is aluminum. The steel strip is 0.10% longer than the aluminum strip. By how much should the temperature of the strips be increased so that the strips have the same length? By the way, I said it's kind of looks like a bimetallic strip, but it isn't. Bimetallic strip is soldered or glued together all the length through that, so that when one of them expands more than the other, they actually have to curl, and that's what you have, for example, in your temperature control, your some mechanical thermostats. That's the way they work on that bimetallic strip. In this case here, they're only bolted together here at the end. That means they can expand independently, and the idea is that this looks exaggerated here. Well, maybe this kind of looks like almost 10% around there, but that the aluminum is expanding more over a given temperature interval than the steel is as it is expanding, and then when the two are done, they're going to reach the same point at the end. So if I do this one here, that the steel expands, for example, to here, there, and then the aluminum as well expands to here, and then the two lengths are equal. And in that case, because they're not glued or soldered together here, they're not curling, they're just expanding lengthwise. Okay, anyway, let's see what we have given. First of all, delta T is what they're asking about. Oops. Delta T, question mark. What, let's see, alpha is given, of course, for both of them. We just looked it up in the book for steel and aluminum. And then we look at delta L and L, 0, and neither one of them is given. They don't say by how much they expand. They don't say what the original length is. They say by how much percentage-wise they expand. And that then means that actually the delta L over L0 says, and actually I take that sentence back. I'm not going to finish that sentence because not even that is given, not even the ratio between the two. What is given is that the, let's see, steel strip, that the L0 divided by of the steel, ST, divided by the L0 of the aluminum, that is given, and it is 0.1% longer. So I'm going to put that 1 right there, and then we can see that this one here is 0.10% longer, and of course this is a ratio here, so it doesn't have units. So that's basically what's given. I wish they would give us actually the original lengths. Apparently we don't need them because the outcome is going to be the same. So for example, if the two strips are each 10 centimeters long, I mean one of them 10 centimeters and the other one 11 centimeters long, or if one of them is 1 meter and the other one 1.1 meter long, the outcome, which is the temperature difference here, would be the same either way, because the aluminum would expand in the same ratio no matter what the original length is. But as I said, I would just prefer to have the original lengths given, because other than that, it's actually going to be kind of some, well, to say the least, interesting algebra. So let me get started on this one here.